Good morning, everybody. I'm Bobby Wright with Becht Engineering. It's my pleasure today to bring a topic dear to my heart for us to talk about. Thank you all for coming from around the world, hopefully. I'd like to introduce my two co-presenters today, Brent Ray from Marathon. Say hey, Brent.
Hello, everyone.
Dave DeWeese from Becht Engineering.
Hello, everyone.
And I want to give a shout out as well to Mike Nichols, who was instrumental in helping set the stage for what we're going to talk about today. Mike actually helped the lead. He was corporate role with reliability at Marathon. And then also a shout out to Gary Guizon, because this is a collaborative effort with not just mechanical folks, but also process and operation folks. Gary leads the corporate Coker SME from a process standpoint for Marathon. So everybody, just wanted to say thank you. This is certainly a team effort. I think today we're gonna start off the first few slides, really just kind of an overview to give you an idea of what we want to talk about today. We all run cokers, so we all see these kind of issues from a day-to-day standpoint, but how do you prioritize them? How do you plan for them? Is it a completely reactive mode, or is there a way to actually get out in front of this? And that's really the foundation for what we're going to talk about today, is how do you get out in front of this and come up with a thoughtful process to assess and improve reliability, and then finally to come up with a plan for better maintenance and turnaround planning. And that's really what led to this project starting in the first place. It really based on a conversation with Mike Nichols and some of his team with Becht's team at the API Inspection Summit in Galveston in 2019. How can you do this? How can you get out in front of it? Marathon went from having 4 sites with cokers to having 7 sites with cokers. So how do you manage all of that information and all of that data, and how do you help people learn from each other? So that's really what gave the impetus for this project that we're going to talk about today. How do you bring together inspection, maintenance, operations, process, and really get people working together? And then from that is to develop, Mike wanted a report that people could look at, that they could plan for where their coker is, where their drums are, in their cycle time, where they are in their life, where they are in their inspection needs, their repair needs, and then most importantly, and really from a capital standpoint, is planning for replacement, because a replacement of cokers, drums, as you know, can be very expensive, anywhere from 50, 60 million to a grassroots coker, 200 million. So how do you don't want 7 refineries coming to you at one point asking for money. So how do you do that? How do you come up with a strategy to work together as a team on site? That's really the critical things. That's the takeaways I want you to get from today, is how do people work better together to manage the asset, in this case, the coke drums. You have process and operations that run the drums. You have inspection, maintenance, and reliability, materials folks that maintain the drums, repair the drums. How do you get people working together as one to do that? And then how do you take that information and come into a long-term strategic plan? That's really what the crux of this program is that we're going to talk about today. We all know, we work on cokers, we've seen hundreds of cracks, we've seen through-wall cracks, we've seen bulges, we've seen squats in the skirts, we've seen leaning coke drums, we've seen drums that the skirt-to-shell attachment weld has actually come unzipped and drums actually sliding inside of the skirt. Those are things that you don't want to have happen. But really with cokers, as we all know, you got to get out in front of that, because if you don't, this is what happens. This slide is one of my favorites. It's also kind of an eye chest, but the things that I want to get across here with this slide is that it all starts with people and how the site works together. And not all sites, I don't know, you guys, how many of you don't have any problems working with your brethren in maintenance or inspection or operations or process? Everybody get along right? Okay, I see some hands where maybe you don't get along. At least that's been my experience, that not everybody works together. So that's one of the things we wanted to fix right off the bat. So we developed gap analysis for both inspection and process, and then mechanical. So it's the process and operations folks. We have two SMEs here at Becht. Mike Kimbrell, we give a shout out to Mike, former retired VP. He's a Becht advisor. And Mitch Maloney, formerly with ExxonMobil, both Coker SMEs, world renowned. And they help lead our gap analysis with the sites to look at how they're doing things, get them talking about maybe creating some best practices. So we did that work, and then combine that work with the inspection mechanical folks, same gap analysis, different questions, and then we got both of those groups talking to each other. And that's really critical. That's one of the things that I think makes this program very powerful. And then the next thing is we actually came up with a tool that Dave is going to talk about to rank the critical factors and how they all, from operation process side to inspection and reliability side, how they all fit together. And then from that, we developed an action plan and long-term planning for the next two turnarounds, yielding at the end when to repair and when to plan for replacement so you can get out in front of these things. And with that, I'm going to turn it over to Dave, who leads our mechanical engineering group here at Becht. So Dave, I'm gonna change the slides for you. So if there's any delay, that's probably my fault. But anyway, take it away, Dave.
Thank you, Bobby. Hello, everyone. I'd just like to start out by saying thanks to all the marathon folks across the sites and corporate that made this a success, and we're absolutely wonderful to work with. I can honestly say this is the most exciting project I've had the opportunity, been lucky enough to be a part of. So thank you. With that, I want to talk about drum critical factors. So it's just one piece of the puzzle that Bobby showed you on the last slide, but it's an important piece. We're going to spend some time on it because those drum critical factors are really the way that we characterize each drum fairly on a level playing field so that we can do comparisons. So those critical factors, they differ by drum region. The key ones that we've highlighted are shell, girth seams, both the cone and the cylinder. The skirt to shell junction is obviously critical, and then the skirt itself, things like keyhole cracking, for instance. So for any one of those regions, we're going to consider some core items, and those are design, fabrication, maintenance, and inspection history. Those are how the coke drum's designed, the quality of the fabrication, the details, and how it's maintained and inspected are all absolutely critical. Possibly even more critical are the operations and process. So how the drum is operated has just a profound effect on the damage it sees and how that damage accumulates. And just as an example, switch and in particular quench practices are critical for that damage. And then the existing condition of the drums is also an important piece for any one of those. So if cracks already exist at a keyhole, they're probably going to propagate faster. Maybe a simpler example is a bulge, which is a stress concentration factor, and damage is going to accumulate in that bulge faster than it would if that bulge was not there. So all of those are factored in for each of the different regions, and we feed that into a critical factor assessment with the goal, as we've been highlighting, to provide planned maintenance and inspection activities, and also to take the opportunity to optimize process and operation if that presents itself. The goal with any of those activities is life extension if you do something. So we want to pull that data and create recommendations that are going to allow the life of the drum to be extended. Some pictures I'm sure we're all familiar with, all kinds of drum damage that we're thinking about, from elephant skin cracking there in the bottom left to some pretty severe bulging courtesy of AZZ. Thank you to the girth seam heat affected zone cracking that we're used to finding as well, and even more exotic things. So what you're seeing at the bottom towards the middle of the slide is actually some pretty severe drill stem damage from the coke cutting process. So just some illustrations that this is a violent, chaotic process with lots of opportunities for damage. So possibly the most important thing is understanding the present condition of the drum so that we can project forward. So that's really our baseline. And it's really the foundation of not only this assessment, but future fitness for service assessments too. It's a comprehensive baseline that allows us to do all of that. And just going into a little more detail for those critical factor designations we talked about a few slides ago. Design, the kinds of things we're looking for are fatigue resistant design, or how you measure up relative to fatigue resistant design, whether you have a constant thickness wall, matching welds, strength matching, drum metallurgy, certainly center feed is an important consideration. So all of those we look at. Fabrication is maybe not as highlighted as it should be, but it's incredibly important, and we did unfortunately see the effects of some substandard fabrication as part of this project. But accurate attention to detail. Is there a blend radius where there's supposed to be a blend radius? Is the crotch radius the proper crotch radius, and does it blend smoothly into the surrounding material? Are the welds ground flush? Was post-weld heat treat performed and performed appropriately? So all of those can have a critical impact on how damage accumulates, because in the end, the damage we're talking about is really fatigue damage, and surface finish and profile can easily have an order of magnitude impact on your life. So really critical details. And then inspection and repair maintenance are also really important. We want to know where the current damage is, and we want to be able to characterize it. We want to know how severe that bulge is, and if that bulge is near a girth seam, so that it's going to interact with it. We want to know what kind of cracks there's been, if they've been superficial, if they've been allowed to grow. And we want to know where those previous repairs are, and how extensive they were, and how they were performed, because that can also have an impact on future reliability. So process and operations is an absolutely critical input. We have a extensive survey that our process SMEs worked with, our Becht process SMEs worked with Marathon process SMEs to develop, and all those folks that I gave a shout out to diligently filled out many pages of data when they had many other pressing things to do. So we thank them for that. But it's not just about collecting data and writing it down and feeding it into the tool I'm going to tell you a little bit more about. It's also an opportunity to learn and optimize and improve daily process and operations. So this was a really important part of shared learning across the sites, and seeing how other people do things in a setting where you're also relating it to reliability and damage, which I think was really powerful. So process SMEs from both our companies talked about steam and water flow rates, how you can get better conversion of feed if there was that opportunity, how you can minimize hotspots through operation, and improving operational consistency. So when we're talking about fatigue, consistency is an important consideration. And we can make additional gains by measuring actual drum thermal gradients and strain and stress. So you can work with higher level parameters, which we certainly do, but the more data you provide through something like a health monitoring system or HMS, the more accurately you're going to be able to characterize what's happening to the drum metal and how that links to damage. I just want to talk a little bit more about operating data before we move on, and how we use that data. and why operating data is so important. So I like to show this image, these two contours on the right. This is from 96 thermocouples. Those are the black dots distributed over a 2.5 foot by 4 foot patch on an actual coke drum. And we contoured those results in a software program and actually animated those histories. Not going to show you the entire animation here, but I did pick 2 points in time, 3 days apart, identical portion in the drum, different times during the quench, where for the same overall quenching procedure, we ended up in one case with a 500-degree cold spot, which you see on the top, and then a few days later, same process again, ended up with a 500-degree hot spot. So certainly a chaotic and somewhat random process. Would be almost impossible to characterize that based on first principles. And that leads you to looking at more of a statistical approach. So the other thing we do, and that we did as part of this project, was develop software to read in HMS data histories, automatically identify the cycles, and then create statistics on the critical factors. So we can go a little bit further than just saying, well, our target quench is 400 degrees or 500 degrees. We can actually come up with what the distribution is, because in coke drum fatigue, it often is the outliers that cause a major portion of the damage. So this is just a way we can leverage that actual data into the assessment. And just to take that a little bit further, we can also not just work with temperature data, but we can actually look at stress and strain if we have that ability, if we have those strain gauges applied to the coke drum. And just an example of variability here as well. On the negative side or the low side of that cycle, we actually are pretty consistent, but on the high side, you can see those peaks in strain do vary quite a bit from cycle to cycle, possibly because there are operational differences, which an HMS can help you look at, or just because the bad spots, the channeling has moved around the drum from cycle to cycle. So perhaps the most important factor in terms of bulging and damage accumulation, it's probably quench, and not just quench, but the initial quench rate, which I think this slide shows really well. This is from RefComm in 2015 in Galveston from PDVSA. And this is kind of showing you, based on HMS optimization, which is in the background that underlies this, how their quench profile changed as they went through that process. So you can see they started with design, and at an hour, they were at 700 GPM. And by the time they got done optimizing, changing that flow rate until they got the strains to reduce in a meaningful way, they dropped that by 600, even more, GPM at that 1 hour mark. So, you know, a factor of 6 difference to get the strains where they wanted. And it shows you that that initial water rate is just incredibly important, after which you can dump as much water as you want in, pretty much. But a good illustration of how you use that data to really improve operations, which is a goal when you do this. This is sort of a graphical overview of the process we've been talking about. And you know, we start with the history, with the data, the surveys, feed that into the gap analysis. Site visit was an important part of all of these, to really talk through that data, talk through gaps in the data itself, and to make sure everyone understands it. But then the next step is to feed it into the actual life cycle analysis, which is what we're going to talk about next, and which is really, as I mentioned earlier, the basis for that level playing field across drums, across different conditions. And in the end, all of that feeds into the action plan and recommendations. Sticking with the life cycle analysis, though, there were, we found 3 keys to success for making this work. One, using industry data. And I just want to step back for a minute. Bobby mentioned Mike Nichols, now retired from Marathon. But this really all started with Mike saying there's got to be a way that I can have some indication of approximately where I am in the life cycle without putting 96 thermocouples and strain gauges on every single drum and doing years of analysis with finite element and data analysis and more complex simulation. I have to be able to have some indication. And so that's really what this was about, taking a relatively simple fatigue model we're going to talk briefly about and calibrating it to industry data. Now, the key to making that work, without a doubt, going through this, was the SME team. So identifying the right critical factors and their relative criticality, so how they affect damage accumulation, so that we could actually successfully calibrate to all this industry data. And not exaggerating, but there are well over 100 coke drums, very far over 100 coke drums and dozens of coker units that are available as part of that to do that calibration. And in the end, what we ended up with was an analytical tool that also pulled that operating cycle data that I showed you a few slides ago and gave that a little bit additional layer of complexity and refinement to feed into that life cycle analysis. Okay, so with this tool, we're combining the critical factors to estimate fatigue damage and progression. That's really the heart of what this is. And as I mentioned, it's based on calibrations to numerous case histories. And the calibration is really based on a model that I'm going to show you graphically on the next slide. But it's based on two key events in a coke drum life cycle that really break up the life into three stages. The first one is when you first start getting initial cracking and bulging that you can notice, let's say, visibly. And then the second key event is your first through-wall crack. Those are important because that data is available going back historically through many decades. It's been identified, perhaps without thinking about life cycle the way we're talking about, but as key events in the history of a coke drum by people going back to the 60s even, because they were recording that data. So that's given us a rich amount of data to work with and to try and calibrate to, which again, I'll show you a little bit more on the next slide. But then don't want to forget to mention that we also want to optimize operation where possible with the goal of maximizing the reliability of the drums, because that's what this is truly about, is maximizing the reliability and the predictability, which we're going to also talk a little bit more about. So how the assessment tool works, this is the graphical representation of what I mentioned. The first dashed line, between 35 and 50% of the cycles to retirement, is bulging and cracking possible. And in our model, that is the breakpoint between stage 1, which is minor problems and very little cracking, and stage 2, which is predictable damage. Cracking and bulging has started, but we're monitoring them, we're repairing them. They're things we can deal with during planned outages. They are not unpredictable and causing unplanned outages, so to speak. That starts to change as we get further into life, about 75% of life, but as little as 60-65% in some cases, depending on how diligent you've been at finding cracks and repairing them. Certainly has a big impact on where that shift occurs. But that it's really when you have that first through-wall crack, that's not the beginning of the end, so to speak, but certainly the beginning of things becoming more maintenance intensive and more frequent shutdowns. And without more frequent shutdowns, certainly a higher risk of unplanned outages. I want to talk about the axes for just a minute. So on the y-axis, we don't have any numbers. We just say cumulative cracks up to many cracks. And to be a little quantitative about that, when we say many cracks at the retirement end of life, we're talking about hundreds of cracks, typically surface cracks with, depending on how you operate, anywhere from just a handful, maybe 3 through-wall cracks, to more than 10 can be possible based on how far you push out that retirement. And that takes us to the x-axis, which again, is not a specific life. That life is going to vary. What that 100% means is going to be different based on what your critical factors are. And Brent's going to talk a little bit more about that. But we can normalize to that retirement life for your critical factors. And all that really means is based on our calibration to actual case histories, that's when people chose to retire the drums, that the maintenance had become more trouble than it was worth, and the economics favored replacement. So all of that feeds into this summary, the deliverables. So what comes out of this, and we've seen this in the circular puzzle piece, and we've talked about it, but the first two steps are the gap analyses for process and operations, and inspection and reliability, and those are critical, and they feed the next two items, 3 and 4, which are the critical factors ranking and risk prioritization, which is what I just talked a little bit about, but also optimization and improvement from the gap analysis, which you don't want to do in a vacuum. That's really about what 5 and 6 are about, taking what you learn from those gap analyses and feeding them into your best practices, your training points, collecting them across sites to truly make them a fleet-wide best practice. And then perhaps most importantly, developing an action plan, a specific action plan for the next 2 turnarounds to hit the reliability targets that you have, which in this case were no through-wall cracks, to make sure that you don't have unplanned outages. And then finally, the last step is to use all of that to develop an economic plan and strategy for replacement. So this has been an overview of the entire process. Right now, I'd like to send it over to my colleague, Brent Ray with Marathon. He's going to talk specifically about how we applied this to the Marathon fleet. And I just want to say thanks to Brent. We've worked quite a bit on this together, and it's been a wonderful experience. So thanks for the opportunity.
Thank you, Dave, and thank you, Bobby. Ditto on that remark. Thank you for the opportunity. This has been a wonderful co-developed strategy, not only externally with Becht Engineering, but internally. So as Bobby and Dave both said, thank you to the internal people and coke drum personnel within Marathon, from the inspection, from the maintenance, from the operation, process optimization people. Thank you very much for helping us with this, because it was a truly collaborative, co-developed process to get us to this life cycle case study that you're going to see. Within Marathon, we took 5 refineries, which represented 25 drums, and we decided to step through each of those refineries and each of the drums and develop this strategy and develop a life cycle of what we could expect on these drums. We do have one other site that has 4 new coke drums, and we didn't use that, but we can use the old data from the old drums to kind of validate some of the things that we are doing. So what we did in this collaborative effort, in the end, we ended up with a near-term, a mid-term, and a long-term plan. We took a look at things between now and the next turnaround. What are you going to plan for at the next turnaround? And eventually this led to planning for a strategic drum replacement. So the whole process comes down to, how do you present this information? How do you take the information that you have gone and talked about, you've debated about, and you've negotiated plans with? How do you present this to management to say, we now have a good plan? Because one of the things we did not have is we did not have a good handle on what a life cycle for a coke drum is. We know that it does get more maintenance intensive the older it gets. We do know that we can repair it and we can keep running and keep repairing. But we also know that there are things with operation that we have to change due to an economic climate or due to other things that are going on in the process that could affect us. How does this all roll together? And so in presenting this to our refinery leadership teams, What you're going to see here is some of the things we worked through on what we call coke drum set C. We had 8 coke drum sets out of the 25, actually out of the 29 if you count the 4 new ones, because we did rank them even though they are brand new. And out of those sets, we developed a plan for each coke drum and for each coke drum set to get us safely and reliably to the next turnaround. And then what do we do beyond that? So in presenting this to your refining leadership team, we decided to go with how's your drum set up? The original construction. How are you looking at these things from a health monitoring system? Are there anything about the design that can be said it's a very good part, such as for coke drum set C, being an egg and cup design for the skirt? That helps with the life cycle. We also took a look at coke production. What type of coke is being ran and how long is it being ran? So all these things add up and they give us a cycle, which is that second bullet point. As you can see, we think with this coke drum set, which is 40 to 52 years old, depending on which drum you look at, this is about an 8,000 to 10,000 cycle life cycle currently on these drums. But we also believe, based upon the operation, based upon design, and based upon how they are physically right now, that we can get up to 12,000 cycles. Again, we tell the RLT that your 16 hours is representative. It's good in comparison to the industry. We also talk about switch temperatures and quench cycles on these. With other drums and other sets, we may talk about different things that affect that life cycle, because not every drum is going to be 12,000 cycles. It can be more or it can be less, depending on how all these factors add up. And the last thing we do tell them is, here's the physical condition we have found. We talk about bulge progression. In this case here, it's average based upon their age. And we also tell them about cracking. Well, cracking in these became an issue later on. Number one, because we introduced some cracking when we welded a new cone to the old cone and added a delta valve. That area became subject to some stresses and such and cracked. Another one, drum, had its first through-wall crack in 40 odd years of operation. That one was also looked at. Why did it happen? What can we expect going forward? And all of this adds up into creating a plan. And all of this adds up for every drum set and being able to rank them based upon that chart that you saw with life cycles that Dave presented. And so as we go forward, let's take a look at those charts. In one chart for the coke drum set C, we were looking at one drum in particular. And this drum, as you can see on the charts, the right side chart is a life cycle chart. The left chart is basically a data manipulation of that data to show you where the age is, what year we expect that age in, and the accumulated cycles, and what kind of life fraction was consumed. We also will give some comments. Maybe that's when the first time you saw a crack, such as in 2018. Or maybe you changed out some plates or did some major welding. We will list that for every drum, trying to see if there's a pattern of the increase or a pattern of things that we can attribute to the way we operate. In the case of this drum at 50 years old in 2019, you can see that we have looked like that we have consumed about 83% of its life based upon that 12,000 cycle number. Comparing that to the right side of the chart, you can see the progression as it goes from 1995 when we were at 24-hour cycles and we changed to 20-hour cycles. We saw some bulging and cracking that increases, but by the year 2001, now we're going to increase the cycle length again or decrease it. And we go from 20 to 18 cycles. So we're increasing damage potential on these drums by decreasing the cycles. And again, in 2010, we reduced it once again. And we're creeping up along and we find things that are going on wrong with these vessels. We find physical conditions that are changing, such that in 2019, we realized we just had a crack the year before. We just had, in 2010, 9 years before, that's when we had a change in the feed entry of this. We are seeing increased damage because of all this. And we realized we are starting to near the end of life. That's why we ranked it in life cycle 3 That's why we think we're at about 83% based upon getting to 12,000 cycles. And that's why you see that last dot in our 2022 turnaround. We think we're going to be up near 90% use. What this chart now allows us to do is to take a look and say, in 2027, we probably should be replacing these drums. And now we can start planning 7 years out, not 18 months, not 24 months, 7 years out. We can take a look and say, what worked well? What is new in industry? What can we do to get a good, reliable, safe coke drum in here in 2027? And in the meantime, what can we do for maintaining the safety and reliability of the coke drum that we have so that we can get a full life cycle out of it? So overall, Marathon, as I said earlier, ranked its drums. And now we have a priority of drums that we're going to go after. We realize that we have a few that are up in the life cycle 3 area that we really need to take a look at. And so we're planning on replacement there. And you go down the list and as you see subset C that we just talked about, we've got a plan going forward for them. We also have plans for D and E, which are in life cycle 2, because we realize we need to make sure that they are operated safely and reliably. We are working with maintenance, with inspection, with reliability, with process technologists, and with operations to make sure that all this adds up. And as you can see in subset C that we've been talking about, there's a strategy. These are the top strategies that we've got for mitigation. We want to work with those groups to collaborate on making sure things happen. We want to utilize the HMS and we want to expand the HMS health monitoring system to make sure that we can optimize the operation going forward and increase the reliability as well as the safety on those drums. And lastly, we are doing the work to look at a replacement strategy. What do we want to do and when do we want to do it so that we can get something new in there that can keep us going, but at the same time, keep the old in there until that time. Again, safety and reliability are the 2 key issues here. So in summary, again, thank you, Bobby, thank you, Dave, thank you, Becht, for all of the work that you did to help us get to this point with our life cycle analysis. Again, thank you internally, Marathon personnel, for giving your input, taking it and applying it and putting it out there for all of us to use in a collaborative manner. We really believe the approach did provide a good structured reliability assessment. It has aided us in optimization of the operation, and it will continue to aid us in the future. It's given us a prioritization of work so that we know when to replace, so we know when to do the work. And like I said earlier, the near term, the midterm, and the long term, and even the shutdown in between are now planned with activities that will help increase the safety and reliability. That proactive planning is very much a strategic item that we need to keep in our toolbox. Taking that away, this life cycle analysis, this life cycle management has now become a coke drum reliability toolbox approach. What are we going to do? We are going to maintain it. When we get on the turnaround, we're going to reassess ourselves to make sure we have that plan going forward to the next turnaround and beyond. But in the overview, this collaborative approach has given us a transparent way to communicate between all these groups to make sure we all understand where we are. Because in the end, we know we have extended the useful life of our drums. We know where the end is. It's given us a proactive plan, and it's given us a chance to look at turnaround and capital spending and maintenance spending on all these drums and on these single drums so that we can be very, very good in knowing what we need to be doing. Overall, as Bobby said, as Dave said, the whole project's brought people together. It's given us a chance to get best practices out for everyone, regardless of its maintenance, operations, tech service, inspection, or reliability. We're all one set on this. It's helped us make better decisions, and it's helped us put a better plan forward. It's helped develop our teams. So we now have a very good plan. All this has become a part of our best practice, and it's all become a good collaborative effort going forward and coming from the past. Again, thank you everyone for this. We hope that what we have given you here today as an audience gives you something to think about and something to look forward to in the world of coke drums, giving us a better way of predicting when we need to replace drums and how we can manage the current life cycles safely and reliably. Thank you very much.
Good job, Brent. I think, Dave, thank you very much. I just want to reiterate, you guys that are watching this, guys and gals that are watching this, please bring your questions. We will have a QA following this presentation, and we'll also bring some of our process SMEs to answer those questions. So please bring that. One last thing, I do just final shout out to all the sites that we worked with. As everybody has said, teamwork's the key. And even though I've not mentioned some of the names at the sites, please know that you were integrally important, and it would not have happened without inspection and reliability and maintenance and process and operations people coming and asking questions and being helpful and wanting to take control of their equipment, for their own sake. And then lastly, one thing to give a last shout out to Mike. One of his key sayings was safety and reliability equal profitability, and hopefully our industry, we will weather this storm and we will be back. Brent, Dave, any last comments before we sign off?
Thanks, everyone.
You guys have a blessed day, and we look forward to your questions. All right, Brent.